Hello everybody. In the last class, we had discussed number systems and arithmetic operation, binary addition, binary subtraction, 2's complement arithmetic. So, we had understood the theory behind the arithmetic operations, addition subtraction operation using binary numbers. Now, in this particular class, we shall look at circuits by which these arithmetic operations can be done. So, it will be extended to next class as well. So, we shall discuss half adder, full adder, ripple carry adder and adder subtractor unit in this particular class. So, first we discuss half adder. Why it is called half? It is because it does not consider any carry from the previous stage. Okay. So, if we are considering addition of two numbers, say 1 0 0 1 and with another number say 0 1 0 1. So, in the first stage when you are adding this number units place, carry is not required from the previous stage. So, there comes the usefulness of the half adder. Okay. And when in the next stage, so this is 0 and this is 0 and a carry is generated from the previous stage. So, basically there are 3 inputs. So, first stage there could be 2 inputs. Okay. So, that is what is half adder, half addition. So, half adder has got 2 inputs A and B, right, and it generates data outputs, which is one is sum, another is the carry. So, this is augend, this is addend, sum and carry. Okay. And we designate by A, B, S and C the way we have seen in this particular block. And what would be the corresponding truth table? So, 4 possibilities at the input 0 0, 0 1, 1 0 and 1 1, and the inputs then corresponding outputs are 0 added with 0, carry is 0, sum is 0, 0 added with 1, carry is 0, sum is 1, 1 0, sum is 1, carry is 0, and when both of them are 1, carry is 1 and sum is 0. Okay. So, how we write it in the form of a logic equation to realize the circuit. So, the carry C is, you can see it is simply A and B. Okay. This is the min term associated A and B, both are having value 1, and sum is obtained, sum bit is obtained with A prime B and A B prime. So, this is your A prime B and this is your A B prime. You sum them up and that is nothing but XOR operation. Okay. So, this is the circuit which is there inside this particular block. Okay. This is half addition. Now, when you talk about full addition, as I have mentioned before, we are also considering the carry input. So, then this particular block will be having 3 inputs. So, the basic data input A and B, that particular addition process and carry that is coming if it is there from the previous stage, right. So, this is the carry in, now we are separating it from the carry out. So, this is the input. So, then there are with these 3 inputs there are 8 different possibilities in the truth table. Okay. So, if you will investigate the truth table for carry in 0, we have what we had seen in case of the half adder. The truth table simply follows the half adder, and when carry in is equal to 1, then we are looking at if carry is in is 1 and 0 0, then the output is 1. This is 1 and one of the input is 1, then a carry is generated and the sum bit is 0, and when all of them are 1, then carry is 1 and the output is also 1. Okay. So, how we write a equation for this Boolean equation for this? So, we can use Carnot map, okay, for minimization, or we can take the min terms and then we do algebraic manipulation, and by that we can find that carry out is A B, A C in and B C in. Okay. If we combine these product terms, we get the carry out, right. So, just we can see for example, when A and B both are 1. So, A and B both are 1 here and here, right. At that time, irrespective of carry in is 0 or 1, right, the output carry out is 1. You can see when A and C in this particular term when A is 1 and C in is 1. So, A is 1 here, okay, and C in is 1 here, C in is not 1 here. So, this is not 1 here. So, A in is here and C in is here. Okay. These are the two cases, right, and both the cases in these two cases irrespective of the value of B, you see the output carry output is 1, right. So, accordingly you can find out, otherwise you can minimize also using standard process, and you can find the carry out is like this. And what about the sum bit? You can again see in this particular truth table when 1 or 3 ones are present in the input combination, in this input combination 1 or 3 ones are present, then the sum bit is sum output bit is 1. Okay. So, that is nothing but a 3 input XOR operation, right. So, that is A XOR B and then XORed with C in, that is what gives you the sum output. Okay. So, then the circuit is simple. So, basically this is the 3 AND gates generating AB, AC in, BC in terms, and that are ORed to get C out, and this is 3 input XOR gate that is generating the sum bit. Okay. So, full adder generation using half adder. Okay. So, if you have got half adder circuit made by someone and several such units are available and you want to get a full adder, what you can do? Okay. So, we can see that 2 half adders and 1 2 input OR gate is sufficient to get a full adder out of it, okay, out of those basic units. So, how we can get that? We can see over here. So, carry out, we have, this is the basic equation, we can write it in this form also. C in has been taken common and out. Okay. So, C in A plus B, right. So, this is odd operation, right. So, this odd operation includes all the min terms except A prime B prime, right. So, when A and B both are 0, that time only the odd output is 0, otherwise odd output is 1 for all other combinations, all 3 combinations. Okay. Then what you do? You take A B prime and A prime B out over here. Why? Because we need the XOR relationship from the half adder to be used in this full adder development, and this C in A B is taken here. So, if you take common, then A B and A with 1 odd C in, that is A B only, right. So, we can see if A and B are given as input, we can generate this term from 1 half adder. This color you can see, this color, right. So, A B over here and A XOR B we can generate by this, right. And then this, the rest of the terms that is A XOR B, which is already generated, to be ANDed with C in here, and for the sum generation this A XOR B is also ANDed with XORed with C in. So, this can come from another half adder block. Okay. So, these A XOR B, these A XOR B output of from first half adder, that is going to another half adder, right. This is the half adder, the XOR input and C in to get the final sum output, and the other input where A XOR B is ANDed with C in. So, this C in you can see that it is getting ANDed with C in to generate this particular term, right. So, these two terms are now available, A B and C in ANDed with A XOR B over here, and you just need to OR them. Okay. So, this is the way we can get it. Now, we have seen 1 bit addition, right. So, if you want multiple bit, say n bit addition, for example, say 4 bit addition, how we go about? So, in that particular case, we need multiple such blocks of full adder. So, inside the full adder we know the circuit that is there. So, that has been seen in the previous slide. So, this is the full adder slide. Okay. So, this is the full adder block, and this full adder block we are using to develop 4 bit addition. Okay. So, what you can see over here is this is each of these full adder this is the first stage, which I said it could have been a half adder also, okay. And then the corresponding inputs are number A with A3 to A0 as different bits, and number B, B3 to B0, 4 bit number are different bits. So, A3, A2, A1, A3, A2, A1, A0 is supplied to one of the input of the each of the full adder, right, and B3 to B0 to the other, okay. And carry of the first stage is fed as carry of the second stage, carry of second stage is fed as carry of the third stage, and carry of third stage is sent as carry of the fourth stage, okay. So, this is the way we normally do the addition, and this is the final carry, okay, right. So, then this whole thing together it will give you some bit, these are intermediate carry, okay. This C0, C1, CT, C2 are intermediate carry. So, the final output will be S0, S1, S2, S3 and C3, okay, the way we have seen it here, right. And if we are using full adder instead of half adder for the first stage, we shall make the C minus 1, the first carry input 0, okay, right. And if it is a block which is to be cascaded with another block, there is a block preceding to it, then that block carry output, which is C3, will be fed as input here. So, previous block carry input will be fed as input to this particular block, okay. If that is to be used in cascade, there are more than 4 bits to be added, and this is the 4 bit unit, right. And if we just look at one example how the addition takes place, say 1 1 1 1 is your A, and B is your 0 0 0 0 1, 3 0 and 1. I have taken this specific example, you can see, right, this is very simple addition, but each of these cases one carry is generated. So, 1 plus 1, okay, this is 0. So, a carry is there. So, carry this carry 1 and 1, this is 0, another carry is there, this 1 and 1, again a carry is there. So, this is the final carry. So, the carry which is generated in the first stage C0, right. So, this again goes as generates C1, C1 generates C2, C2 generates C3. So, as if it the carry ripples through each of these adder, that is why it is also called ripple carry addition, okay. This is the maximum distance it travels, so as to say maximum path, okay. Now, if we remember how we conducted 2's complement arithmetic. So, subtraction we got by addition, okay. So, how did we do that? We got a negative number of the original number by taking 2's complement of it, and what was 2's complement? It was inversion, that is 1's complement, then plus 1, okay. So, remembering remember that concept of 2's complement arithmetic, and we can see how in the hardware we can implement subtraction 2's complement by 2's complement method by using a adder circuit. So, now what we have got, this is the 4 bit full adder, okay. So, within it there are 4 individual 1 bit adder, and we have already seen before how a 1 bit adder is made using basic logic gates, right. So, this 4 bit adder has got this 2 input add and oggend, okay, and this is the sum output and this is the final carry, okay, right. So, the subtrend, the one that we want to subtract, we pass it through a bank of NOT gate inverter, okay. So, at this point we get 1's complement, right, and then we need to add 1. Now, you can see the C minus 1, we made it the first stage full adder, which could have been half adder just for the addition purpose, unless it is cascaded or so. But here you can see when we want to use this as a subtractor, right, then we need to add 1. So, that 1 can be fed here, okay. So, automatically we do not need to have any additional thing to do. So, instead of this carry in, we put a 1, right, which is doing the 2's complement of the number B. It is used to get the 2's complement of the number B, okay. then we add, then we see the result and we interpret the result based on the carry and other things, the way we have seen it before, right. And so, how we I mean we let us see the example. So, 15 minus 1, right. So, 15 is your 1 1 1 1. Remember that the here we are using the these 4 ones. So, the sign bit over here is implied, that is the 0 over here, okay. And 1 is your 0 0 0 1, right. So, when you take one's complement of it, so this is 1 1 1 0, right, and then you add 1. So, what you get over here 1 1 1 0. So, this is a carry that is getting generated, we shall discard it, and if you consider the the in this case the sign bit, then this will be 1 and then finally, there will be a carry generated, right. So, these are implied thing, the sign bit over here is implied, right. Okay. As long as it is within the range, we have no issue. So, this is this 1 1 1 0 is your final answer. So, if you convert it to decimal, it is 14, right. Now, we look at how we can get within the same arrangement, same framework, both addition and subtraction. Okay. So, for that what we are doing, we have placed an example of 8-bit adder subtractor. Okay. So, 8-bit adder subtractor. So, you have got 8 full adders, right. So, this is one full adder 1 2 3 4 5 6 7 8, you can see 8 full adders there, and the numbers are A0 to A7 and B0 to B7, right. So, this is the way the numbers have been placed, right. Now, you see one thing, that this B number B0 to B7 is passing through an XOR gate, and one of the input to the XOR gate is connected to an external input. Okay. So, this external input we are representing as sub, standing for subtraction, right. So, when you put it 0, right, that means no subtraction is taking place. So, it will be normal addition, right. So, when this is 0, XOR gate, we know the XOR relationship, any input XORed with 0, it is the input itself, right. So, at this point, at the output of the XOR gate, right, what will come? It will come the number B itself, right, B7 to B0, that will come, and then this is 0. So, this will come as a 0, right. So, it will be a normal addition, standard addition. Now, instead if we have got sub is equal to 1, that means we are interested in doing subtraction. So, subtraction is when it is 1, of course, this carry, so called carry, here it will become 1, and Bi XORed with 1 is Bi prime. So, you will get inverted inversion of B over here, complement of B, 1's complement of B, and 1's complement of B and added with 1, we get 2's complement, right. So, then those 2's complement gets added, and then the normal output, the way we have seen before, or we understand how 2's complement arithmetic takes place. So, it will be A plus minus B, that is A minus B. So, this is a single adder subtracted unit, which is performing both the job of addition as well as subtraction, depending on what you give here as input. If input is here is 0, this is addition, input here is 1, it is subtraction, right. Now, we shall look at 2 examples how it happens in the hardware. So, we look at a addition example to start with. So, the numbers that we want to add is 90 and 50. Okay. So, in decimal of course, and then the corresponding binary equivalent you have to get. So, this is your 90, okay. This is your A and this is your B, right. So, this is your 64, right. This one represent, this is 16, 64 and 16, 18. This is your 8, right. 64 plus 68, 80, 80 and 88, and this one is representing 2. So, 90, right. So, this particular number is 90. So, this you will put as A7 to A0. So, A7 to A0. This is how this blue one that you can see A7 0 1 0 1 1 0 1 0, that is how it is placed. Is it okay? And then 50, right. So, 50, for 50 what we are doing, we have to convert first it to binary. So, this is your 32 plus 16, that is 48, and this is your 2, that is 50, right. So, this is in a different color. So, this is your B0, B7 to B0. So, 0 0 1 1, you can see 0 0 1 1 and 0 0 1 0. So, this is what is placed here, right. And since it is addition operation, so this input over here will be 0, this carry input here is 0, and what will be the corresponding XOR output? So, this is 0, the same number will come over here 0 0 1 1 and 0 0 1 0, and for the other input of the full adder will be the same as what the original number is, of course, because there is no such case of inversion. Now, if you perform the addition, you can see what is happening, intermediate carry and the final carry that will be generated and the sum bits. So, 0 0 0 over here. So, this intermediate carry output is 0 and sum is also 0. So, this is 0, this is 1 and this is 1, right. So, sum is 0, this carry is 1. So, this 1 0 0 for the full adder. So, this is 1 and carry is 0. So, 0 0 1 that gets added. Okay. So, sum is 1, carry is 0. So, 0 1 1 for this particular full adder, So, sum is 0 and carry is 1. So, this carry 1 1, these two sum bits, the two bits addend and oggend bits. So, 1 and 1. So, this is 0 and carry is 1. This 1 0 1, this 3 getting added. So, this is 0 and this is 1 and 1 0 0, this is finally 1 and the carry is 0. So, this is the number that you will get 1 0 0 0, 1 0 0 0, 1 1 0 0. What is the value? Right. So, this is your 64, after that it is 128, this is 8, 36 and this is 4, 40, 140, clear? Okay. So, we shall look at one subtraction example, right. So, the same 90 and 50 is the original A and B we start with, so that it becomes easier to understand. So, this is your 90 and this is your 50, right. So, A is placed as 90, this is the blue colored one that you can see, right, and 50 is the brown colored one. So, that you can see over here, that is how the 50 is placed. Now, the subtraction is input is 1, because we want to do the subtraction. So, the carry in over here for the first adder is 1. Okay. So, this, because of this 1, there will be an inversion taking place for the XOR gate, because 1 and 0 XORed is 1, right, 1 and 1 for the second one. So, this is 1 and this is 1, XORed is 0. So, this is the way for the rest of the things, right. So, this is how the full adder input will be now looking like, okay, for each of these full adder. Now, if you perform the addition, so this is 1 and this is 0, right. So, if you just add them up, so this is 0 and carry is generated as 1. Okay. So, this is 1 0 1, these 3 are added. Okay. So, the sum is 0, carry is 1. So, 1 1, sum is 0, carry is 1. 3 1, sum is 1, carry is 1. 1 0 1. So, this is 0, carry is 1. So, 1 0 0, 1 0 0, sum is 1, carry is 0. Then these two are 1 and 1. So, sum is 0, carry is 1, and this is 2 are 1 1, sum is 0, carry is 1. Is it fine? So, this is the number. So, this one that is we are getting here, we discard it, and this is what you get, and the answer we know that it is negative. So, basically this is representing that the number is this one is getting discarded. Okay. So, if you have the concept of sign bit here, so this 1 will add with that sign bit, this will become 0 and there will be a 1 here, that 1 will get discarded and this value will be 0, sign bit will be 0, right, if we include the implied sign bit here, right. So, this is the answer. So, answer here what we see, this is 32, right, and this is 8, 32 plus 8, this is 40, clear. So, this is how we do addition and subtraction and from the basic circuit that we have seen. So, to conclude, half adder adds 2 binary digits to generate sum and carry. Full adder also considers carry input. Full adder also considers carry input from previous place and thus has 3 inputs and 2 outputs. Okay. A full adder unit can be obtained by 2 half adders and 1 additional OR gate. In ripple carry addition, carry output of one full adder is connected as carry input of the next full adder, and subtraction can be done by full adder circuit by 2's complement method. Here 2's complement is achieved by a bank of NOT gates and making the carry input 1. And finally, a full adder and a bank of XOR gates for the subtrahend addend input can give a circuit that can perform both addition and subtraction. Okay. So, this is what we have seen in this particular class. Thank you.